Hi everybody. In this unit we will learn about chemical equilibrium. This is chapter 7 of your book, and it talks about all the chemical reactions that are reversible. So we've been talking about chemical reactions since ever. We talked about a chemical reaction um, that is you have H2 plus O2 to yield H2O. So if I have how to balance the equations and how to classify the chemical reactions. We talked about energetics, whether it is exothermic reaction or endothermic reaction. We talked about activation energies. We also talked about reversible reactions and forward reactions. So in this story, we will talk about a reaction that goes both directions. Not all the reactions are reversible, but most of them are. So the story that we're going to learn today is that if we have A plus B that is yielding C plus D. So this is with one arrow, that means the reaction is going forward. So it's forward going reaction, it's one direction. But if I draw an arrow backward as well, I can do double arrows like this, or I can do A plus B. I can say, hold on, C plus, something is wrong with it. Hold on. Okay, so let me just try it again. So I want to have A plus B that yields C plus D. What I wanted to say is that I can have double arrows, or I can have an arrow, the half arrow, that direction goes this way or direction goes this way. That means it is a reversible reaction, that my reactants are producing products, and at the same time my products are converting back into the reactants. Okay, so that's a reversible reaction. So today we will learn how a reversible reaction works. And once the rate of the forward reaction is equal to the rate of the reverse reaction, we use a term equilibrium. So to understand the term equilibrium, let's take an example of container that has water in it, and you're heating that water. And I am going to assume that this is a closed container. Okay, so I have water molecules all over this here, and as you start heating it, the kinetic energy increases. They're moving faster and faster. They hit each other, and they get enough energy that they get bumped up with each other, and they some maybe this atom will kick this atom so strong that it's going to jump up to a gaseous state. So water starts evaporating. So in the beginning, there is more water and there are less vapors. Now the vapors that are here, which is gas particles, they're also hitting each other. Okay, and as the number of vapors increases, because you're constantly heating it, there are more collisions. We learn about collisions in kinetics. So if there are more, the concentration increases. So as the concentration increases, the probability of colliding them together is going to increase. So if there are too close together, they're going to hold each other, slow down, and convert back into the liquid. So eventually what happens is that there is water that's turning into steam, and then there is steam that's turning back into water. And a point comes that the speed or the rate, okay, of forward reaction becomes equal to the rate of the reverse reaction. And this situation in a closed system, okay, in a closed system is called dynamic equilibrium. Dynamic equilibrium. So dynamic equilibrium is that your rate of the forward reaction, okay, rate of the forward reaction is equal to the rate of the reverse reaction. So the ratio does not change. So if the rate, when we calculate the ratio, we divide it, rate of the reverse reaction and rate of the forward reaction. does not change, so ratio remains the same, so we call it equilibrium constant, where C is the concentration. Okay, that means the concentration of the reactants or products doesn't change. Speaking of concentration, we need to talk about then an equation. Okay, so if I have A moles of chemical A and I have B moles of chemical B, which is producing C moles of chemical C and D moles of chemical D. Here, these are the coefficients, okay, the molar ratios, the concentration. So when I'm writing my equilibrium constant, the concentration of the products is, it has to be concentration of the products divided by the concentration of the reactants. So I will say C, and I take it as a concentration. I told you that whenever I write something in the parentheses, it is concentration. And it is to the power of the number of moles. And then I have D, and take concentration to the power of the number of moles of D divided by A, concentration of A, you know, my reactants, divided by the power of my reactants. I don't like this tablet. Okay, let me try it again. And B moles of B, C moles of C. So I'm calculating concentration, the equilibrium constant. It has to be the products. Okay, these are my products to the power of the number of moles divided by my reactant, the concentration of the reactants to the power of the number of moles of the reactants. Okay, so this ratio does not change. So if I am producing all together, let's say 10 moles here, then those 10 moles are producing like maybe 10 moles here. So the total, the concentration of forward and the backward reaction doesn't change. The ratio is the same. There is no unit force for the equilibrium constant because it's a ratio. Okay, so it doesn't have any units. So to give you an example, if I have the ammonia, there is a Haber process. You will see in this chapter it talks all about Haber process, the production of ammonia, the very common industrial process. Haber is basically an industrial process to produce ammonia. You don't need to know any more than that. So if I have nitrogen that reacts to hydrogen to yield ammonia, okay, it is a reversible reaction. So to calculate the equilibrium constant, I will take the concentration of products, okay, to the power of the number of moles of the product divided by the concentration of the reactants. You see that I have only 1 mole of nitrogen, okay, so it's only 1, and then I have 3 moles of hydrogen, so I'll take it to the power of 3. So if I know the concentration, the actual concentration, let's say I have 0.3 molar this and 0.1 molar this and 0.2 molar this, I can calculate the value of the equilibrium constant. So now you need to learn what is equilibrium. So first of all, the definition of equilibrium is that the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so there is it stays constant. In a closed system, it is called dynamic equilibrium, where no change happens. The net change is 0. So whatever the products you're making, the products are converting back into the reactants. So you're not really getting anything out in your hands. And then you need to know the equilibrium law. Okay, the same thing one more time. The law of equilibrium, the law of chemical equilibrium states that at a given temperature, the ratio of the concentration of the products to the concentration of the reactants is constant. Okay, so this what, excuse me, oh, I'm not even writing anything. So when we calculated this Kc, that is the law of equilibrium, the equilibrium constant that we calculated. Okay, so it's in your book. I want you to read that. You have plenty of time over these snow days. So I want you to read that. What is the law of equilibrium? What is equilibrium constant? And how do you calculate the ratio? So when we are calculating this equilibrium constant, you must understand that you are going to ignore your solids and liquids. The pure solid and pure liquid will not be written down in your equilibrium expression because their concentration does not change. Okay, so the you need to read a paragraph that talks about heterogeneous equilibrium and solubility. So it says that a saturated solution in a closed system will establish a dynamic equilibrium, and that means again this, the forward and reverse reactions are the same. And in any chemical system, we do not count the solid and the liquid states. Okay, so let's say, let me see if we move on, and I will teach you when we get there. So the concept of equilibrium I have explained already. So let's say I have dinitrogen tetroxide, which is decomposing into nitrogen dioxide. So in the beginning you have all the reactants, and you see only few products here. Okay, so most of all you have is the reactants, and you have only few products here. But as the reaction processes, as the reaction move on, you see that the ratio of your reactants and the products does not is pretty much the same, because it is converting into products, and products are converting back into the reactants. So chemical equilibrium occurs. Where is my pen now? Chemical equilibrium occurs when a reaction and its reverse reaction process at the same rate. So I will not repeat it over and over. So here is a graphical representation of a chemical reaction. You have time. So with time, you understand that the concentration of the reactants is going to decrease. The concentration of the products earlier, in the beginning of the reaction. So in the beginning of the reaction, concentration of your products increases, and the concentration of your reactants decreases. But eventually a point comes that you have enough of the products that they start converting into reactants. So eventually you see that the concentration of the reactants and the products become equal. Okay, so the equilibrium is achieved right here. So once equilibrium is achieved, the amount of each reactant in the product remains the same. So there is no output. Okay, whatever you put in from one side, it converts into, it comes back to it. So equilibrium can be reached from either direction. Like you can go from reactants to products, or you can go from products to reactants. That doesn't really matter. Okay, equilibrium can be achieved either way you want it. So what it shows here is that either your nitrogen is playing more of a role to yield ammonia, or hydrogen, however you explain it. Like both of the nitrogens and hydrogen are the reactants. And this is the ammonia is a reactant, and these are the products. Okay, so the concentration of products increases, reactants decreases, and eventually they have ammonia. Or the concentration of the here, this is the reactant, these are the reactants, this is the product. So product increases, reactants decrease, and eventually they kind of equalize. It doesn't really matter whether we start from the reactant and product. We will have the same proportion of the three substances in the equilibrium. So catalyst has the same effect. We have learned that catalyst can speed up the reaction because it lowers the activation energy. But it doesn't really matter. You have forward reaction, you have forward reaction, or you have reverse reaction. That doesn't really matter. The catalyst will help it both way. Catalyst will speed up the reaction no matter which direction you want to go. So equilibrium is achieved faster, but the equilibrium composition remains same. So the amount of the reactants and the products remains the same. So let's calculate the example I was giving you. We have a general reaction. This is how you calculate the equilibrium constant. Products, it has to be products over reactants. Okay. And if I give you, there is an example. So to calculate the expression K, I have ammonia that reacts with oxygen, so it's combustion, producing nitrogen monoxide and water. So you see that you have 4 moles of ammonia. So I have a concentration of, let's start with the products. It's products over reactants. So I have 4 moles of nitrogen monoxide and then 6 moles of water. So you see here that I have the mole comes here, the 4 moles come here, divided by the reactants. Here is the 4 that goes up here. Okay, there are no fixed units for K. You must determine them based on the expression because it's a ratio, so there is no unit for it. So if I am given the concentration, how can I really calculate it? But before we do that, it says we ignore solids and liquids. So when, let's say I have a solid here. So to calculate this, instead of saying that it will be NH3, okay, um, HCl over NH4Cl, products over reactants. Since my NH4Cl is a solid, okay, since my NH4Cl is a solid, I am going to ignore it because it does not make any play any role. We ignore solid and liquid because they do not have molarities or pressures. Okay, so my equilibrium constant here will only depend on the products, this part here. So if this is pure solid or this is pure liquid, okay, I'm just going to ignore it. So here is the ammonia process again. If I'm given the values of nitrogen, hydrogen, and ammonia, I can definitely calculate the equilibrium constant. So equilibrium constant again is going to be the value of ammonia, which is 0.1, and it's 2 is the number of moles because I have 2 moles of ammonia, and then I have 0.5 moles of nitrogen, and then I have 0.3 moles of hydrogen, and I have 3 of those. So when you calculate these numbers, you get this. So this is how you calculate the equilibrium constant. What does the value of K actually means? So if my K is bigger than 1, because if you understand, it is the product over reactant. Okay, so now the common sense tells you, if I have a bigger number here and a smaller number here, okay, my answer is 3. So if the K is 1 or larger than 1, that means my reaction is favoring the product. So I have more products than reactants. Okay, so the reaction is about to complete, or it's in the process of completion because I have more products. If I reverse this, okay, if I have products over reactants, and here I have 2 and here I have 6, of course it will be in decimals. Okay, so it is less than 1. That means my reaction is in the favor of reactants. So the reaction has more reactants in it than the products. Okay, so you need to keep this in mind, that if the K is greater than 1, the reaction is product favored. So there is more product than the reactant. If it is less than 1, the reaction is reactant favored. So this is what the K tells me. The ratio, the Kc of nitrogen or in any chemical reaction at a constant temperature and pressure does not change. It remains the same. But if you change the temperature, the concentration will change, and it will change the Kc as well. So you need to keep that in mind. So equilibrium can be reached from either direction. I explained that earlier on. So here is the data that proves that it doesn't matter which way you come, you can reach the equilibrium regardless. Okay. The next thing is, how once the reaction has reached its equilibrium, how can I change it? How can I stress it? So that phenomena was explained by Le Chat. We call it Le Chatelier's principle. So Le Chat is the name of the scientist who gave us the concept of stressing the equilibrium. So he said that if a chemical reaction is at equilibrium, okay, so I have the Haber process of producing ammonia. So assume it is a endothermic chemical reaction. It means it has 170 kilojoules right here. Let's do it. It's actually, hold on one second. Let me erase it. Let's do delta H as negative 92 kilojoules. So this is exothermic chemical reaction. So you see that 1 mole of nitrogen and 3 moles of hydrogen is yielding 2 moles of ammonia. And it is a reversible reaction. So I assume that right now the reaction is in equilibrium, that these reactants are producing the products and the product is dissociated, decomposing back into the reactants. So Lishat said that if the chemical reaction is at equilibrium and you go ahead and stress it, okay, you want to go ahead and stress it, the reaction will react in a way that it can relieve the stress. So reaction would like to relieve the stress. Now, how could you stress it? I can stress it by the concentration. I can add more than what I need to add. I can stress it by pressure. I can stress it by temperature. Okay. The catalyst does not stress it because catalyst is helping it both directions. So basically, this process will explain that if the chemical reaction is at equilibrium, and you want to go ahead and disturb it, okay, then the reaction will automatically shift. We use the word shift in a direction that it can relieve the stress that you have provided. Now we are going to go ahead and see how can we stress it by concentration, pressure, or temperature. As I said, the catalyst does not make any difference because catalyst help it both sides. So, but anyway, that's the Le Chatelier's law that you need to understand, that a stress placed on a system at equilibrium will cause a shift to minimize that stress. So here we have, so when this seesaw is balanced, that's when it's at equilibrium. So if you push it on this side, like you pressure it on this side, eventually this will go down, okay, and they will come back up. So that's what it is. Let's say I have a chemical reaction here. It is an endothermic reaction. Heat is being added to the reactants, and I have the products. And you see that you can do the reversible reaction like this. You can do the reversible reaction like this. It doesn't really matter. Both of that means it's a reversible process. So what happens if we add water? So well, water is on this side. Okay, what happens if I add calcium chloride, or I add acetone or silver nitrate or heat or cold? So the rule is that the reaction will shift away from what you add, and it will shift towards what you take away. So this is the effect of concentration. Okay, this is how the concentration will shift the reaction. So let's talk about the effect of concentration. Like, how can I stress it by concentration? If I add the nitrogen, as I said, this was the rule. The rule is that the reaction will shift away from what you add. Okay, you need to understand that. The reaction will shift away from what you add. Okay, and it will shift towards what you take away. All right, so let's go back. So the reaction is going to shift away from what you add. So if I add nitrogen, the reaction will shift to the right. So it will produce more products. All right, it will produce more products. Once it's produced more products, eventually the concentration of the products will increase. And once that concentration of the products increases, it will start producing more reactants. So eventually the reaction will stabilize at a different stage of equilibrium, because the purpose of this reaction is to attain the dynamic equilibrium. So yes, that equilibrium will change where it was before when you stressed it, but later on the reaction will automatically adjust itself to regain the equilibrium at a different level. So my point here is that if you add the nitrogen or hydrogen, the reaction will shift to the products. If you add, on the other hand, ammonia, the reaction will shift to the reactants, because if I have more of this, it's going to produce more of that. So the reaction will shift that. What if instead of adding, okay, I want to take away something? Okay, so if I want to take away the ammonia, like there is no more ammonia, so the reaction is going this way, and as soon as ammonia is produced, I take it out. So there is no ammonia to go back to the reactants. So the reaction will only shift towards this side. Okay, on the other hand, if I take away nitrogen, okay, So ammonia is producing nitrogen and hydrogen, but as soon as I take away nitrogen, the hydrogen cannot combine with anything to produce ammonia. So the reaction cannot go favor this way. So the reaction will only go to the left. So again, the point is that if you add something, it will shift away from it. If I take away something, it will shift towards it. So what happens if we add ammonia? So if I add ammonia, the reaction will shift to the left. Okay, more reactants. What if I add nitrogen? Then the reaction will shift to the right. Okay, what if we remove ammonia? So as I told you again, removing ammonia means I cannot go this way, so the reaction will only go this way. So this is how the concentration affects. Let's see the effect of temperature. So what if it is an endothermic chemical reaction? If it is an endothermic chemical reaction, okay, it needs heat. So if it needs heat and I heat it, okay, it will produce more products because I'm favoring it to go in this direction. So adding the heat in an endothermic reaction, adding the heat will favor the products. Okay, and if I cool it down, so going this way, it is exothermic. So because in this direction it is endothermic, okay, and in this direction it is exothermic. So if I'm cooling it down, okay, I'm favoring exothermic chemical reaction. If I'm heating it, I'm favoring endothermic chemical reaction. So this is what you need to understand when it comes to temperature. But changing the temperature also changes the Kc. You have to understand that. Because if I add more heat, it produces more products. Okay? So if it produces more products, the Kc is products over reactants. Right? So if it produces more products, the concentration of the products increases, my Kc will become, okay, bigger than 1, and that means it will be a favor to the product. So the Kc does not change when I change the concentration, but Kc, the equilibrium constant, does change if you change the temperature. So this equilibrium constant is only good at a constant temperature and constant pressure, so keep that in mind as well. So that treat the heat energy as a product or a reactant. So same thing again, I have its product right here. So these two combine to give you this. So if I'm heating it, I'm favoring it this direction. If I'm cooling it, I'm favoring it this direction. So that's all you need to know. Rule: an increase in the pressure. So the third one is the pressure. An increase in the pressure means you are squeezing them in. So if you increase the pressure, okay, they are getting close together, so they will shift towards less number of moles. Like here I have 2 moles, and here I have 4 moles. So what is the effect of pressure? How would the reaction will relieve the pressure? So if you increase the pressure, the reaction will shift towards less number of moles. If you decrease the pressure, the reaction will shift towards higher number of moles. So this is what you need to understand again. So this is the effect of temperature, pressure, and concentration on equilibrium. This is Le Chat's law. Le Chat said that if this reaction is already at equilibrium and you go ahead and stress it, it will work or do something to relieve or minimize that stress. So you need to understand how the effect of concentration, temperature, and pressure work. Let's see what is left here. Hold on. What's wrong with it? Okay. And so we learned about temperature, pressure, concentration. So industrial process, this is the Haber process that it talks about, that we really need to know this equilibrium and how equilibrium works to increase our percent yield. Okay, the Haber process is the transformation of nitrogen and hydrogen into ammonia to create ammonium-based fertilizer. So there is a lot of detail on Haber process. There is no rocket science in it. On your page number 186 of the book, so all of you need to read page number 186 to read the details that how nitrogen and hydrogen combine to produce ammonia, and Haber was the scientist who gave us this concept. We need to have the optimal conditions. We need to know how to add reactants and remove the ammonia. This has to happen at higher pressure, colder temperature because it's a gas. Okay, this is how the whole thing works. So this is just a regular process. There are not too many questions that how to make this work, but you actually need to understand what it is, and that's about it. So that kind of completes your equilibrium reaction, equilibrium unit, or equilibrium chapter, I should say. These are just examples that you need to work on. I will update the packet in your Blackboard class. So you need to work on the equilibrium chapter. Okay, equilibrium chapter, which is number 7, and equilibrium packet, that's in your Blackboard. We will work on this together, only the answers. I will not work on it together in the class. I will only answer your questions if you have any. So before I see you, you need to work on kinetics completely and equilibrium, okay? Because I missed you guys on Wednesday, and then Friday we had a snow day. So we missed 2 classes. So I want to make sure that we don't miss any time. I will also post some labs to make up our kinetics and equilibrium lab. It will be the Gizmo labs that you can do online. So you can print it and complete the lab and bring it to the class whenever I see you. In case we don't have a class Monday and Tuesday, I will also post acid-base lecture, and you need to take notes on that as well. So this way we are not wasting any time, even if we are snowed down. So all right, anybody, I will see you in class whenever I see you. Thank you. Bye-bye.